All right, Honors Chem, we are going to do yet another day of Hess's Law, but this time we're going to use it a little bit differently. Now, I want to bring you back to this example that we did in example 6 right up here. Now, we did this reaction where we had 2 sodium bicarbonates, otherwise known as baking powder to you guys, going to sodium carbonate, carbon dioxide, and water. We use this reaction all the time to create those carbon dioxide bubbles when we're baking to make our breads and our sweet cakes rise. That's, sweet breads and cakes use this all the time. So notice when we got the heat of this reaction, we had to deconstruct everything that was on our reactant side into the atoms that made that, and then construct everything that was on our product side and add up these heats of formation from the table. Now that gets super tedious to construct and deconstruct everything. So there's a simpler way that we can do this instead of using our systems of equations. Okay? The systems of equation method will always work, but as you can see, it can be super tedious. I'm going to teach you the shortcut. There's a shorter way that will always work and accomplishes the exact same purpose. So here we go in the shorter way. This is the summation equation using Hess's law. So the heat of the reaction is equal to the sum. Remember, sigma in Greek means the sum of. So this is the sum of all the heats of formations of all the products minus the sum of all the heats of formation of the reactants. Now remember, we have to multiply our products and our reactants by their respective coefficients in the balanced equation, okay? So we still have to pay attention to the balanced equation coefficients. Because if there's water in an equation, for example, if there's 4 waters, we have to multiply that heat of formation of water by 4 because there's 4 waters. Okay, so we have to pay attention to those coefficients when we're summing things up. So we add up all the products, those heats of formation, we add up all the reactants, all those heats of formation, and we take the products, we subtract the reactants, and that will give us the heat of the reaction. It's a lot easier than constructing and deconstructing everything. Okay? So, here we go. We're going to do this on a couple of these examples here. So we're going to use the short version of Hess's law to calculate the heat of combustion of ethane. Okay, we're going to write the chemical equation. So if we're doing combustion, do you guys remember combustion? We are always combining it with oxygen and creating, do you remember? Carbon dioxide and water. Okay, so we have ethane, C2H6. We're going to combine it with oxygen. And we want to know when we create that carbon dioxide and water, what we're going to get. Now, usually when we have combustion, we have water coming off in the gas phase, water vapor. So remember, we have to be really careful about some of the states of these. And this will also be a gas. Okay, so first things first, we're going to balance this equation. Okay, so let's balance this. So 2 carbons, right? 6 hydrogens. So I'm going to need to multiply that by 3. 2 times 2 gives me 4, plus 3 gives me 7. So I'm going to do 7 halves. And this I can do fractions because, that's right, we're going to do 1 mole of this. So fractions are okay. Okay? So we're going to use our table that we've got. And I've linked a table to your homework assignment. I'm just going to be scrolling back and forth to the table. So we need the heat of formation for our products first. Remember, delta H of a reaction is the sum of the heats of the products minus the sum of the heats of formation of the reactants. Okay, so our products are carbon dioxide and water gas. So we're going to look at carbon dioxide. So carbon dioxide, we have, let's see, carbon dioxide. Do you guys see it? We've already done it. So negative 393.5. And we have water in the gas phase. So we're going to actually use this one, negative 241.8. Okay? So let's set that up. So I have 2 carbon dioxides. So carbon dioxide was negative 393.5. And sometimes I like to put this on top so I know exactly what it is. Plus, and I've got 2 of the water in the gas, or not 2, I've got 3 of the water in the gas phase, negative 241.8. And that's my water. Okay, so there's my products. And then I'm going to subtract my reactants. And I've got one ethanol, or not ethanol, ethane. So let's look for ethane, C2H6. So C2H6, let's find that. C2H6, did you guys find it? Right there, ethane, 84, okay? And why am I not looking up the heat of formation for oxygen? Do you remember? Heats of formation for elements are always 0. So the oxygen is going to be 0. Okay, so here we go. Let's get back to my pen. So I've got negative, and it didn't switch. Got negative 84.0 for my ethane. And I can also do 7/2 times 0 for my oxygen. Okay, so I'm going to add this up in my calculator. So if I do this, so 2 times 393.5 times 2 plus 3 times 241.8, I get a negative, and boy, it's not going to let me write. I get a negative 1,512.4 kilojoules there. Okay, and notice on my product side or my reactant side, I just have 84. But when I do a negative of a negative, it becomes a positive. So I'm going to have negative 1512.4 kilojoules here. Negative of a negative is a positive, plus 84.0 kilojoules here, because 7/2 times 0 is still 0. So when I add that up, now notice both of these go to the 10th, so I can go to the 10th. So when we're adding, we are going to go to the least accurate place value. And since both of these are to the 10th, I can go to the 10th. So this would give me negative 1428.4 kilojoules for that reaction. Okay, that needs to be a 1, and that 1 looks terrible. Okay, so let's do another reaction this way. So I've got sodium hydroxide, okay? And if I look at this, I'm going to still look at that same table that I have. Okay, let me get my notes really quick. And I didn't do them. Actually, I did. Okay, so sodium hydroxide. We want the sum of our products. Remember, I'm going to take this. So delta H of that reaction is the sum of the heats of formation of all our products minus the sum of the heats of formation of all our reactants. Okay? So first things first, we're going to make sure that this is balanced, and it is balanced. So we've got sodium chloride in the solid. So if I look at my table, I have negative 411 for my sodium chloride. So I'm going to have negative 411.2, and this is my sodium chloride. Now I got this on the table previously. You can use your table and scroll up and verify that I have it correctly. So that's my sodium chloride plus my water. Now notice I'm getting the water in the gas phase. So that is negative 241.8. Okay, so there are my products, and now I'm going to subtract my reactants. I've got sodium hydroxide. So sodium hydroxide, I've got negative 425.8 kilojoules, and I've got hydrogen chloride. And hydrogen chloride is negative 167.2 kilojoules. Okay, so when I add this up, I get a negative 653.0. Notice these both go to the 10th, so I can go to the 10th, minus, and this gives me a negative 593, and this I can go to the 10th as well. So I have a minus, so that actually becomes a plus. So my heat of formation for this will be a negative 60.0 kilojoules. And yes, I need to go all the way to the 10th because both of these go to the 10th. Okay? One last example. I've got 2 hydrogen sulfides plus 3 oxygens going to 2 waters in the liquid state at this point, and 2 sulfur dioxides. Once again, I'm grabbing these values from the table that is in the previous couple pages. So my sulfur dioxide is from the table. That is a negative 20.6. I'm just going to put them underneath here. Remember, oxygen, because any element, the heat of formation for that element is going to be 0. So that's 0. Water in the liquid state is negative 285.8. And sulfur dioxide is a negative 296.8. Okay, so those are the values that I gained from the table that's in the previous page. Okay, previous couple pages previous. Now, we want the heat of the products. So that heat of the reaction is the sum of the heat of formation for the products minus the sum of the heat of formation for the reactants. Okay, so we're going to look at these products first. Now notice they both have coefficients of 2 by them. So I'm going to have to multiply them by 2 because I've got 2 of each of them. So for my water, I have 2 of my negative 285.8. And for my sulfur dioxide, I have 2 times my negative 296.8. Okay, so there's the heat of my products. Now let's look at my reactants. So I'm going to subtract the sum of my reactants. So my reactants, I have 2 hydrogen sulfides, so 2 times negative 206, right? Oh, and that just went down on me. So negative 206 point, is that 2? No, 20.6, not 206, 20.6. I'm reading my notes wrong. Sorry. So 20.6. And I have 3 for my oxygen. And oxygen is 0 because it is an element. Okay? So my products, when I simplify that, let's see, 2 times negative 285.8 plus 2 times negative 296.8. That gives me negative 1165.2 kilojoules for my products. And my reactants give me 2 times 20.6 gives me a negative 41.2 kilojoules. Now a negative times a negative becomes a positive. Okay? Or negative of a negative is a positive. So I'm going to take 1165.2 and I'm going to add the negative, the negative 1165.2, I'm going to add 41.2 to that. So when I do that, I get the heat of reaction to be negative 1124.0 kilojoules. And yes, that 0 is significant because both of these go to the tenths. So I need an answer to go to the tenths. Okay? So that is how you use the heat of formation table to use the summation equation for Hess's law. And it's a lot easier, I think, than the systems of equations. But when you have reactions that you don't have all the information for, sometimes you do have to use the systems of equations, and it's also a useful tool to know. So hopefully this makes sense. If you don't understand or you have some questions, please come and see me in class during Flex or email me. See you later. Bye.